Okay, this is Mr. Peterson, and I'm going to do page 3 of the 2.4 Part A notes. And if you saw the first installment here, you'll know that a negative underneath the square root sign is the number I, and that the square root of 36 is just 6, so we're going to say 6i here for our final answer. Notice that the I is behind the whole number, okay? All right, the next one here, the negative underneath the square root sign is the number I. The I number is actually the square root of -1, and that's like a -1 times 12 there. So the 12 breaks up into 4 times 3. Let me show you how you could get that if you weren't sure about that, which probably is not going to happen with a small number like 12. But you can type it on your calculator, and then you go to your table settings, make sure it's in automatic mode with a start value of 1. Then you go to your table, and you want to cruise down the right hand side till you get to the first perfect square, which is 4. 4 times 3. The square root of 4 is 2, so when we're done here, you're going to have 2i and the square root of 3 in the back. And you can see the proper order here, I in the middle, but whole numbers in front, square roots at the back. So these next 3 are just simply putting those in the right order. Whole number in the front, I in the middle, square root in the back is the proper order. So I'll do the same here. The I has to go in between these two. And here the -8 belongs in front of the I, but the square root of 5 belongs behind it. So this is the shortcut way of writing -8 times I times root 5. And you treat it all as one thing, -8i root 5. Okay, this leads us into a brave new world. We're going to expand your number system and make it look really weird. Okay? We're going to look at complex numbers, and complex numbers are numbers that are put together with 2 parts. So I want you to write 2 parts here instead of more than 1 part. Complex numbers are made up of real number parts. Here the a value that we're going to have is 3. That's the real part. Sorry, let me write real correctly there. And the format is a plus bi. So the imaginary part is what we call the back here with the I in it. The number in front of the I is called b. So here b equals 4. And what this is one number with 2 parts to it. Just like your hand is made up of fingers and thumb, but it's all one hand. Okay? And then down here you have a complex number, so all that's being asked is what's the a? The real part here is just the number -6. You've been using that number for many years. And then this imaginary part in the back has a front part of it of 7, so the b value is 7. On this one, the real number part is -5. We always call that a. And the number in front of the a, we could write this like this. It'd be a little more clear. Is -1. So the b is -1 in this problem. Now this one here is backwards. The -12.3 is the real number part, and it belongs up front. So I'm going to fix this one. And once it's in the proper order, the value of a and b are pretty obvious here. A is the real number part, which is -12.3. Now the imaginary half of it is at 6i, but the b is only the part in front of the I. So don't include I when you're putting b down. So that's a and b. Now, complex numbers include all of the numbers that you've learned so far in school. All of the real numbers you know. For instance, there's 12 eggs in a dozen. So, for instance, 12. You could write it like this, 12 plus 0i. And it's a really strange way of writing 12, but it's still 12. 14.5 could be written as 14.5 plus 0i. And these complex numbers really help us to solve equations in Algebra 2. They're also useful for electrical engineers designing circuits, and the other place where they're used a lot is predicting weather conditions. Okay, so if you have just an imaginary part, let me show you. We had an answer like 6i up at the top of problem 9. Then you could write it in complex mode by putting a 0 in front this time. So the real part zeroes out, and 6i could be written 0 plus 6i in complex format. Same with this one here. This could be written as 0 plus 3.5i. And I took an electronics course when I was at Widener University back in the 80s, actually. And I had to use these numbers every day in that circuits course. So these are very useful numbers. You may not ever become an electrical engineer or a meteorologist, which are the two main areas these are used. But you are a high school student, and high school students use this in Algebra 2 to solve equations. So you'll use it in the immediate future. All right, so that does it for page 3 of the 2.4 notes. And I pick you up on the other side for the first half of page 4.